so let's see shortly why for unitary matrices we have that all the eigenvalues in their absolute value equals to 1. So the core idea that we must remember is that unitary matrix, or let's call them also orthogonal matrices in the real space. So unitary and orthogonal matrices, they have the property that their eigenvalues absolute value equals to 1. So remember that by definition, an orthogonal matrix and a unitary matrix, they both preserve the norm. So by definition, if I take the norm of a unitary matrix, let's call it Q, or orthogonal matrix, let's call it Q, with a vector V, any arbitrary vector V, you'll get that the norm of this equals the norm of the vector itself without the Q, because again, they preserve the norm of a vector. So this is a very important property. Now remember the property of the eigenvalue. So if you take a matrix with its eigenvector, it equals eigenvalue times the eigenvector. And the last property is the definition for an orthogonal or unitary matrix, which is Q self-conjugate Q equals I, okay, or Q transpose in the real case. So now you remember that QV equals V by norms, but also you can say that QV equals lambda V because this is definition for eigenvalues and eigenvectors. But if you look on the norm of lambda V, because lambda is a scalar, you can take it out in its absolute value, right? So you get this one times the norm of V. Now equalizing the two statements that you got, the two equations that you got, what you get that the norm of V equals absolute value of lambda times the norm of the vector V. Now we took an eigenvector. By definition, for an eigenvector, the vector is not the zero vector. Therefore, the norm we are talking about is not zero. Namely, it's greater than zero. But what is important, because we are going to divide, that it's not zero. Therefore, I can divide the norm of V equals absolute value of lambda norm V, because those two left sides are equal. So I can divide them by V, by the norm of V, and get that the absolute value of lambda equals 1. And this is the proof that for a unitary or orthogonal matrix which satisfy that preserve the norm, we get that all their eigenvalues in their absolute value equals 1. Now, in the real space, it means that the eigenvalues are or positive 1 or negative 1. But in the complex space, it means that all the eigenvalues lie on the circle, on the unit circle. Okay, so the conclusion is that for any orthogonal matrix, or unitary in the complex case, all the eigenvalues, they have absolute value of 1, and that's it.